During the first video, I covered the syllabus and talked a little bit about what geologists do. The second video, I started with chapter 1. We talked about some people you needed to remember for this first test. And those people are um, that German guy, Alfred Wegener, who came up with the theory of continental drift in 1912. That was real important because that led to plate tectonic theory by 1967. We'll talk about that in more detail in Chapter 2, because Chapter 2 is entirely about the theory of plate tectonics, the most important theory in geology that you're going to learn. Theory of plate tectonics shows you the beauty of science. When you get one theory that works in explaining almost everything that occurs on planet Earth and inside of the Earth. Isn't that beautiful? Where you get one theory that's been tested over and over again, and it always works. It tells us why we have mountain ranges, why they are where they are, how do the Appalachian Mountains form, how do the Rocky Mountains form, how do the Alps form. It tells us why we have volcanoes, why we have earthquakes, why do the continents fit together like pieces of a jigsaw puzzle, why do we find oil and natural gas and coal and minerals where we find them. It's all explicable. It's all understandable if you understand this one theory called plate tectonics. So watch out for that next couple days. Subscribe to my YouTube channel. Videos 4, 5, and 6 are going to talk about plate tectonic theory. We also talked about another person you need to remember, and his name is Charles Darwin. He came up with another important theory called the theory of biological evolution. Evolution means change with time. Everything changes with time in nature. You're different than you were 5 years ago. Your generation is different than your parents' generation. We don't live the same way that we did during the time of the 13 colonies or during the time of Christ. Things have changed. Countries change, people change, the earth changes. It's nature. Things change, and that's what evolution means. We'll talk about that more later. The other person we talked about that was real important is Nicholas Copernicus, who back in the year of 1432 came up with a theory of the first heliocentric view of the universe, showing that the sun is at the center, and then the earth just revolves around the sun, as do the other planets. Prior to that, we had geocentric views of the universe from people like Aristotle. Two more people we need to talk about before we start talking about this important person. And this important person, by the way, is James Hutton. But we want to talk about two other people first, though. Let's talk about Johannes Kepler. There he is, Johannes Kepler. He's a German scientist, and he made astronomical observations using pointers. We talked about pointers last time. And he came up with laws that explain how the heliocentric universe works. He showed that the moons revolve around planets. We have a moon revolving around our planet. Jupiter has dozens of moons revolving around it. And they orbit in ellipses, elliptical orbits. These orbits are not circles, but they're like squashed circles. So sometimes a moon will get closer to a planet, and sometimes it'll go farther away. The same with the Earth. Sometimes, since the Earth revolves around the sun in an elliptical orbit, it gets closer to the sun sometimes and farther away from the sun during its 365-day orbit around the sun during every Earth year. So Kepler's astronomical observations using pointers showed that the heliocentric view is the only logical view of the known universe, which at that time just consisted of our solar system. We now know that it consists of a lot more than our solar system, but we're talking the 1500s to the early 1600s. Another person who lived around the same time as Johannes Kepler was Galileo Galilei. Galileo, it says here he was an Italian astronomer. That's not really true because you probably know that Italy as a country did not exist until 1891. So he was actually he was a Venetian astronomer. But anyway, he was the first one to develop a telescope to look into outer space. And he observed the moons of Jupiter. He carefully studied the heliocentric and the geocentric view. And by the 1500s and 1600s, all of Galileo's astronomical observations pointed to a heliocentric view of the universe. And it was supported by this new invention called the telescope. If you take my historical geology class later on, we'll talk more about these people because I've only given you the basics of their stories, which is quite interesting. I mean, their lives are interesting and how they got to where they made these great scientific contributions is amazing. But let's talk about this next person that you need to know for the next test and for the first test, and his name is James Hutton. You must remember this guy, James Hutton. And James Hutton is the father of modern day geology, or the founder of modern day geology. He's the one who started the science of geology. And his name is James Hutton. We're going to talk more in detail about Mr. Hutton. These pages are loading slow for some odd reason. But in the 1700s, he came up with there he is, James Hutton. He came up with a new theory that is the foundation of modern day geology. And it's so important, I'm going to write it down so you won't forget it. And it's called Uniformitarianism. Uniformitarianism. Don't forget, James Hutton, the founder or the father of modern day geology, came up with this principle of uniformitarianism, which is what every scientist around the world keeps in the back of his or her mind when you're doing geology. And it's a two-part idea, this theory of uniformitarianism, and it changed the world. The first is that it can be summarized by this one phrase, the first part of this idea. The present is the key to the past. What does James Hutton mean by that? In his principle of uniformitarianism, James Hutton says the present is the key to the past. So, in geology, we're interested in studying the past. And I mean the distant past. We now know that the Earth is 4.6 billion years old. And the universe is 13.7 billion years old. There's overwhelming evidence to show that, and I'm going to present it throughout this class. But remember those numbers. So we're not interested in, for the average person, you might think the 1950s was a long time ago for you. Or maybe going back to the 1920s when Calvin Coolidge was president, that was a long time. Or George Washington's time was a long time ago. Or when Caesar was assassinated outside the Senate during the first century, that was a long time ago. That's not a long time. That's a blink of an eye in geologic time. We're talking about millions and billions of years. How in God's name are we going to study events that have occurred millions of billions of years ago. We can't travel back in time. There's no such thing as a time machine. As Stephen Hawking put it, I don't think there ever will be a time machine in the distant future. And his rationale was if if time travel was possible in the future, where are all the tourists from the future? I haven't met any of them. Have you? Has anybody? So we're probably not going to be able to travel back in time to see what happened. The only way we're going to learn about the past is just study what's going on now. And what does that mean? Well, let's say you and I we go to some beautiful place, such as the Big South Fork here in Tennessee, and I've been there many times. The Big South Fork, we go there and we see stacks of sedimentary rocks, and it looks like this. We see all these beautiful rocks here, and we're sitting here and we're looking at these rocks. We're trying to figure out how did these rocks form. Well, we use James Hutton's principle of uniformitarianism to figure it out. We go here and we look at these rocks very carefully and find out, first of all, what kind of rocks are they? Well, they're layered, so they must be sedimentary. We know that. And later on, I'm going to show you that this rock is called limestone. It's made of a mineral called calcite. And we can identify it by bringing a little bottle of acid. Acid will, if we drop acid on this rock, it's going to fizz, effervesce. And we find this is limestone. And we find fossils, evidence of past life in these limestones. And the fossils we find are let me show you what kind of fossils that we find there. We find corals, like these beautiful coral fossils inside of the limestones. Well, there's our clues there. The rock is limestone. It has coral fossils in it. So, and then we date the rocks. We figure out how old they are using chemical methods that I'll talk to you about later, or by looking at the fossils themselves. We find out that the rocks are 320 to 350 million years old. Well, now we know that these rocks were formed 320 to 350 million years ago. Well, James Hutton's principle of uniformitarianism is what solves the problem for us, because now all we got to do is look for places around planet Earth today where limestone is forming, and it always forms in the shallow ocean. So that means that sea level is higher, and this area was covered by a shallow ocean. And those coral fossils tell us that the weather was tropical, like the Caribbean or the Florida Keys. How do we know that? Because corals live in warm, shallow, clear, sunlit waters, like in the Bahamas. So there was a Bahamas-like environment here 320 to 350 million years ago. Principle of uniformitarianism. We identify the rocks, and we look at the fossils if there are any, or other clues in the rocks. And then we look for places on planet Earth where those same rocks are forming today. We assume that the laws of physics and chemistry acted the same on planet Earth in the past, and therefore we can figure out what the Earth was like at every location on the planet in the past. Did that make sense? So, principle of uniformitarianism, the present is the key to the past. To study the past, we look for modern analogs, how similar rocks are forming today, and then we could assume they formed that way in the past. That was the first of James Hutton's big accomplishments. There's another person, but when I talk about the principle of uniformitarianism, I can't talk about it without talking about this other person who came before James Hutton, and you need to know about him, and his name is James Ussher. Another James to remember. James Ussher. This is James Ussher. He was an archbishop in the Presbyterian Church. We have lots of Presbyterian churches here in the great state of Tennessee. And I'm sure you know that the Presbyterian Church is the Church of Scotland, just as the Anglican Church is the Church of England. Anyway, James Ussher was the head or the Archbishop of the Anglican Church. And Scotland's part of Great Britain. The King of England, Henry VIII, wanted to know how old the Earth was. He asked James Ussher. James Ussher went through the book of Genesis, and he figured out that the Earth was formed, believe it or not, at 4004 BC. So James Ussher said the Earth was formed at 4004 BC. There it is. Where does this idea of a 6,000-year Earth come from? It comes from James Ussher. It's not biblical. I've read the book of Genesis many times as a Christian, and I don't agree with, nor do most Christians agree, that the Earth is 6,000 years old. But James Ussher did. He said the Earth was formed at 4004 BC, and he came up with an idea called catastrophism. This was the main idea scientists had as to how the Earth formed and when it formed prior to James Hutton. The Earth was formed by a catastrophe that occurred, catastrophic events that occurred at 4004 BC, October the 10th. And it hasn't changed much since. This does not match up with this geologic record or basic science. And in fact, most Christians don't believe in the 6,000-year-old Earth. This idea doesn't make sense if you believe in science. James Hutton said the Earth was not formed 6,000 years ago, but its history, in his own words, went so far back in the past that it cannot be viewed. That's how old geologic history is. He realized the Earth cannot be 6,000 years old for many different reasons, but one of them was he looked at the rocks in Scotland. He was a farmer, and the rocks on these coastal bluffs were thousands of feet high, and they were made of sandstone. Sand is one of the rocks we're going to look at. And he noticed there was a creek that flowed through his property and flowed into the sea. And it was depositing sand at a thickness of about 1 millimeter a year. A millimeter is about the thickness of a dime. He did the basic math and figured out, if that's how sandstone forms, and that is how sandstone forms, then those cliffs can represent millions of years of time, not thousands of years. Common sense will tell you that there's rocks underneath those coastal bluffs. So there must be at least tens of millions of years. We didn't really know how old the Earth was until a scientist we'll talk about later on, and her name is Madame Marie Curie. Madame Marie Curie, Française, she's French. Actually, she's not French because her parents are from Poland, but she is a naturalized French citizen. She discovered a way to figure out how old the Earth is. We now know the Earth is 4.6 billion years old. James Hutton, so his theory of uniformitarianism, why is it so important? Giving him the title, the father of modern day geology. First, we now have a way of studying the past. The present is the key to the past. And we also know that Earth history is unimaginably long, not produced by a catastrophic event that occurred 6,000 years ago, by, but by everyday geological processes occurring over enormous amounts of time, hundreds of millions of years, billions of years, unimaginable amounts of time. So Hutton's ideas are the basis of modern day geology. And um, so this first chapter has a lot of different people's names. There's so many people, but I'll give you a few more to remember. Next person is Sir Charles Lyell. Who is Sir Charles Lyell? Well, as you can tell, he's a Sir. So he was knighted by the Queen. What Sir Charles Lyell said, he published these books called The Principles of Geology, in which he clearly put together all. James Hutton, you know, he wasn't a very good writer. He wrote in a very obtuse way that was hard to follow. And so many people didn't read his book about uniformitarianism. I'm sorry. So, but what Charles Lyell did is he made the first geology textbook called Principles of Geology, in which he put together James Hutton's ideas and he applied them into the real world and various geological studies in a way that people could understand it. And so his textbooks that were printed in the early 1800s were the first geology textbooks. They are now under a glass case at the Yale University's Science Library. And so his great contribution is promoting this principle of uniformitarianism so it was widely accepted, and also for producing the first geology textbooks. I hate to ask you to remember all these people's names, but there's no way around it. Next two people we need to know. Please don't forget these two people. Harry Hess and Robert Dietz. Who are they? Well, excuse me. Back in 1962, they came up with a theory called sea floor spreading. And this theory of seafloor spreading, introduced in the year of 1962, showed that the sea floor spreaded apart, moved apart, like two conveyor belts moving apart. And the continents are on these plates, so they can move as the sea floor spreads apart. Since the continents are contained within here, they can move apart. That's how the continents move. They conclusively showed that Wegener was right. So by 1962, people would realize that Wegener was right. There was a lot of debate before 1962. And the last person you need to remember for this chapter, his name is Tuzo Wilson. There he is, Tuzo Wilson. And what he did was he combined seafloor spreading with continental drift from Alfred Wegener in 1912 to come up with a theory of plate tectonics. This new theory explains how the Earth works. Let me show you, and I'll show you more detail in the next chapter. But the Earth's surface is divided into these plates, and these plates can push against each other, they can pull apart, or they can slide next to each other. And wherever the plates meet, you get earthquakes. Wherever the plates meet, that's where you're going to find oil and natural gas. So let's take a look here. Tuzo Wilson said that the Earth is divided into these plates. And where you have these red lines here, those are the boundaries of the plates. Here you can see the Pacific plate, the Australian plate, Indo-Australian plate, the Nazca plate, the South American plate. Looking at this diagram, look at it for a moment if you would. Tell me where the United States is. What plate are we on? 99% of the 95% of the United States, or actually 99% of the United States is on one plate. What plate is it? We're on the North American plate. Everything from Seattle to beautiful Miami to my home state of New Jersey to Kansas, Tennessee is all on the North American plate. The only parts of the United States that are not on the North American plate are Hawaii, which is on the Pacific plate, and Southern California, which is on right on the edge of the Pacific plate. Even God's country, the land of milk and honey, paradise on earth, Coalfield, is on the North American plate. All right. Anyway, where the plates meet, we call them plate boundaries. These red lines are plate boundaries. And that's where the plates either push against each other, pull apart, or slide next to each other. Regardless of what they do, they're going to make earthquakes as the plates bump against each other, pull apart, because there's energies going to be released where the plate boundaries are. We're going to find that 95% of the Earth's action occurs at these plate boundaries. Earthquakes, volcanoes, oil, natural gas, precious metals all occur where plate boundaries are. But the plate boundaries weren't always like this, so we have to find the ancient plate boundaries to find natural resources as well. So don't forget Tuzo Wilson, 1967, plate tectonics. Harry Hess and Robert Dietz, 1962, seafloor spreading. Alfred Wegener, 1912, continental drift. The study of geology is the application of using the scientific method to study the Earth. And we do it for many different reasons. As I mentioned before, to protect the environment, to locate, extract, and manage natural resources. Our standard of living depends on us finding natural resources to manufacture products, including your cell phone and your computer, requires hundreds of different minerals. The drywall in your house, all this drywall in this house, if you have an old house that's made of plaster, it's all made of minerals. It's a mineral called gypsum. So we need to extract these natural resources to maintain our standard of living and protect our environment at the same time. What's that called? It's called sustainable development. And we also, the third thing that geologists do besides extract natural resources and protect the environment, is we want to predict and also reduce the effects of natural disasters, such as earthquakes, volcanoes, and flooding, and landslides. So a lot of geologists end up working for FEMA, for example. Why study geology? Well, we've got to find these natural resources. We have a huge national debt. We need to, if we, I understand the cause, and I'm sympathetic to the cause of protecting the environment. I'm an environmentalist. I like to have clean water and clean air, and I think everybody does. You don't want to go to Norris Lake and swim in pollution or garbage or disease-infected water. The public deserves that. We should keep our water and our air clean, and geologists work on that. But we can't be so extreme that our environmental laws are such that our companies can't compete with foreign companies and making our products more expensive. In other words, we do have to have a mining industry. We do need to drill for oil. If we don't do that, we're going to have to import that from foreign countries, and our deficit's going to go up, and we'll be sending our jobs overseas. We want to keep those high-paying jobs in the United States, and let me give you an example. If you take the extreme approach and say we shouldn't drill for oil anywhere in the United States because of global warming, and I, that is, I'm not extreme. I'm not saying that global warming is occurring, and we do need to cut down our use of fossil fuels, but we cannot do that at the moment because the non-renewable energy resources, the renewable energy resources, such as solar and wind, are too expensive. In other words, we have to have oil for the next couple of decades. And if we have our environmental laws so strict that we shut down all of our oil drilling in the United States, we'll be sending our money overseas. Our deficit's going to go up. We're going to lose those high-paying jobs. And there has to be a middle ground where we can protect our environment and also extract these natural resources, in my opinion. When we talk about natural resources, we have non-renewable resources and renewable energy resources. Non-renewable energy resources are like oil or minerals or coal. There's just a limited amount. Once we use them up, they're gone. Now, a renewable energy resource like solar or wind or timber is basically, it'll last forever. I mean, with timber, we can cut down trees, but we can plant more trees. With wind, the wind is going to continue. The solar is going to continue for billions of years. So these are called renewable energy resources. These non-renewable energy resources are part of national security as well, because if we shut down the U.S. oil industry, we're going to have to import oil from the Middle East, to Saudi Arabia and Iraq and Iran and all these countries that sponsor terrorism. We need to instead be pumping the money into our own economy. So yes, we need to reduce our dependence on fossil fuels to combat climate change, global warming. But we can't be so extreme to say that we're not going to drill for oil at all in the United States. That would be an economic disaster for the country. There has to be a middle ground. Same with mining. It says here mining to release heavy metals. Yes, that's true. But if we don't mine, we have to import it from other countries. And therefore, people are going to lose their jobs. People need to make a decent wage in this country. So I think there's a middle ground there. We can protect our environment and extract natural resources. We can do it in an environmentally safe way. Natural hazards. People die every year from landslides, earthquakes, tsunamis, floods, volcanoes, and sea level rise due to the global warming. So we need to fight this. We need to predict when we're going to have earthquakes, how likely they are to occur, so we can build buildings that aren't going to fall down with big earthquakes. Or if there are landslides, there's things we can do to prevent landslides. I do a lot of that. A lot of geologists do side work, and I do a lot of consulting work. So natural hazard mitigation and prediction are important. A lot of jobs in that as well. When we talk about the Earth, we talk about systems. And I'm going to try to get a picture of this for you. Um, so let's show you how that works. Nowadays, here in the year 2020, we look at the Earth as a system. And what does that mean? Well, let me show you a picture. It might help. Somebody once said, "A picture is worth 1,000 words." I think he was correct. Um, when we talk about the Earth as a system, there are four four spheres or four spheres or four parts of the system, and they are the biosphere, the atmosphere, the hydrosphere, and the geosphere. Those are the four parts of the Earth's body. The Earth is a system: biosphere, atmosphere, hydrosphere, and geosphere. The biosphere includes all living things, from bacteria to animals to plants to funguses. They're part of the biosphere. Biologists study life. Bio means life. Atmosphere is the gases above us, and the oxygen you're breathing right now. And there's nitrogen in the atmosphere. There's argon. There's water in the atmosphere. The clouds are up in the atmosphere. Our weather occurs in the atmosphere. All of that is held. All these gases are held close to the Earth by Earth's gravity. That's the atmosphere. The hydrosphere includes all of the water on planet Earth, including rivers, lakes, groundwater, water underneath the ground, and in ice in the glaciers, and 97% of the Earth's water is salt water in the oceans. That's the hydrosphere, water, the sphere of water. The geosphere is the solid Earth. It includes the crust. I'm sure you learned about that in high school. Then the mantle, the outer core, and the center of the Earth. You have the inner core. These four spheres interact with one another. And the best way to think about that is think about the human body. The human body has a circulatory system where your blood circulates. You've got your bones, that's another system. Your muscular system, your nervous system, which sends signals between your brain and through your spine to the rest of your body. All of those spheres interact with one another to make a healthy you. If one of those systems shuts down due to cancer or disease, you die. Well, the Earth is the same way. The hydrosphere, the biosphere, the geosphere, and the atmosphere interact with one another. They're not separate. For example, um, if you have the formation of more clouds, you have more rain, and then that's going to affect the hydrosphere, right? It's going to affect the level of the water level in rivers and lakes, and that's going to affect the biosphere, isn't it? Because living things are affected by how much precipitation occurs, and that's going to affect the geosphere because as the rivers flow faster, they're going to cut into the rocks, erode the rocks, wear them down faster. So everything is connected to each other, and that's why we consider the Earth to be a system. The next thing we're going to look at is called the rock cycle. And here it is, ladies and gentlemen, the rock cycle. Soon we're going to be talking about rocks. I'm sure you've all heard about geology, a lot about rocks. Well, you need to know there's three kinds of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. Then what are minerals? Well, step one in this class is you need to know a rock and a mineral is not the same thing. Rocks are made up of combinations of different minerals. If you think of a chocolate chip cookie, that would be the rock. And then the chocolate chips, those are one mineral. And the macadamia nuts, they're another mineral. You know, the different ingredients, each ingredient is a different part of the overall rock. So rocks are made up of combinations of different minerals. There are more than 3,000 minerals known to man. So in order to study rocks, we have to study minerals first. There's three kinds of rocks: igneous, metamorphic, and sedimentary rocks. Let's talk about them one at a time, and later on we're going to talk about them in great detail. And then we'll be able to understand this rock cycle. So igneous rocks, igneous means born of fire. That means that these rocks were once molten. They were once liquid. They were at temperatures from 600 to 1,500 degrees Celsius, about 1,000 to 2,200 Fahrenheit. They were molten. They were liquid, and then they cooled to form igneous rocks. So igneous rocks are formed where the temperatures are very high enough to make a liquid. Sedimentary rocks, what are they? Sedimentary rocks are layered, and they're formed at the surface of the earth. In every single environment that you can think of, you can form sedimentary rocks. And rivers form sedimentary rocks. For example, the sand flowing through a river might get deposited at its mouth in sandy layers, which will become sandstone. Limestone, we talked about it. It forms in the shallow ocean. Sedimentary rocks form in lakes. They're formed by glaciers. They form in the deep ocean. They form in deserts. They form in glaciers. Our northern neighbor Canada has a lot of glaciers where the ice deposits sediment into layers, and so sedimentary rocks are formed at the surface of the earth in every natural environment, and the geologist always has to figure out where do these sedimentary rocks form. Metamorphic rocks are formed by metamorphism. If you look in the Webster's dictionary, it means change. These are rocks that have changed. The implication behind that is, the implication is quite profound. That means they were something else, and then they changed to what they are now. Metamorphic rocks are rocks that have changed due to one, two, or three of the following. One thing that can cause a metamorphic rock to change is an increase in temperature. Another is an increase in pressure. And third is the presence of hot fluids, usually hot water. So metamorphic rocks are rocks that have changed due to an increase in pressure, an increase in temperature, and or the presence of hot fluids. Notice I didn't say a decrease in pressure or a decrease in temperature. An increase in pressure, an increase in temperature, and or the presence of hot fluids. They were something else, and they changed into what they are now. It's important to note that when you increase temperature, if you increase it too much, it's going to melt, and you're going to make an igneous rock. So a metamorphic rock, if temperature is involved, the increase in temperature causes the rock to change in the solid state. It changes without melting. So now we know the three main kinds of rocks: igneous, metamorphic, and sedimentary. And we know that rocks are made up of different kinds of minerals. There's another word that you have here that you need to know: magma, M-A-G-M-A. Magma is liquid rock. Okay, magma is liquid rock. Let's take a look here and see how the rock cycle works. If you heat up rock, it's going to melt and it's going to make a magma. The magma cools and crystals come out and it makes an igneous rock. Now, these igneous rocks can be broken down by water, wind, or ice, worn down, and that's called weathering. So these are broken down into little chunks, pieces that are, they could be sand-sized, they could be pebble-sized, a little bit bigger, they could be silt, smaller than sand, or they could be clay, which is even smaller. But they're broken down into little pieces, and these pieces are called sediments. These sediments can be transported or moved by water, wind, or ice. Usually it's water. Imagine that a river is cutting through the rocks. And it can it tear apart those igneous rocks, break them down into little chunks of sand and gravel, and carry them downstream. And then eventually, the sediment that's transported is going to be deposited. It's going to be laid down in layers, and these layers of sediments we call beds. So the sedimentary beds might be deposited at the mouth of a river, like the Mississippi River, for example. Layers of sediment. After these layers of sediment are deposited, laid down, and then another layer is going to be laid down on top of it. Another layer is going to be laid down on top of it. So eventually, that layer is going to be deep underground as it's buried by younger and younger layers. And so these layers on the bottom are going to get pushed. They're going to be compressed or pushed on by the overlying layers, and that might squeeze them together to form sedimentary rocks, so that the sand becomes sandstone, or the silt becomes siltstone, or gravel becomes conglomerate, or whatever. So sedimentary rocks are formed. Now, eventually, these sedimentary rocks are buried by younger and younger rocks. Now they're deep underground. The deeper underground you go, the higher the pressure and the temperature. The deeper in the earth you go, the temperature goes up. That's why South African